Hi and welcome to another lesson in the physics video series. Today we're going to be discussing elastic forces and potential energy. We're going to start by discussing the force required to stretch a rubber band or a spring, and then of course the potential energy that's stored in that elongation. Okay, let's get started. Before we can explain any of the mathematics that you see here, we first have to set up the situation as follows. Here we have a simulation where we have a spring which will be grasped by this claw. When I squeeze this claw, that will allow me to pull this spring and elongate it. This green dashed line is the center line known as the equilibrium position line. The spring does not want to pull to the left of this line when it is at this position. However, when I squeeze and drag to the side, you can see the spring wants to recoil back to the original equilibrium position. Let's take a look at the vectors that are involved here. When I pull back with an applied force, the orange vector pointing to the right is being reacted against by the spring's restoring force. This is the force that the spring returns in equal and opposite direction to my applied force. Also, as I pull to the right with this applied force, you can see a green arrow appear, and this is the displacement. That's the stretching distance from the equilibrium position to the place I pulled it. This slider bar is called the applied force, and that is what I am pulling with. However, this spring constant, which is set at 200 newtons per meter, is something that needs a lot of explanation. So we're going to switch the screen to the math page, and we're going to talk about what is a spring constant and what do these values indicate. For this lesson, we're going to use equation 15 and eventually 16 from the physics reference table. Equation 15 is the spring elastic force equation known as Hooke's law. And equation 16 is the potential energy stored in a spring. You'll notice that force equals some letter K times X. K is that spring constant and X is the elongation. The potential energy also relies on K and elongation. Let's talk about K, what it means, and how to derive it. As we mentioned before, Hooke's law for the restoring force of a spring is given as F equals Kx. Technically, it's negative Kx because the force pulls in the opposite direction as the applied force. This is the force for the spring. The spring always restores against the motion. The spring always pulls against your applied force, so that is why there is a negative in the equation. The absolute value drops to negative, and we just talk about the magnitude of the spring's restoring force. So here we are at that moment where we will now discuss the value of K and its meaning. Its basic meaning is elasticity. The spring constant K is derived very simply by dividing this X underneath this force. So K is equal to F divided by X. The spring constant is actually a ratio of the applied force that you pull on the spring with to the elongation that it experiences. So we call this the pull to stretch ratio. It's very easy to understand what K is now that you see it as a ratio, pull to stretch. So for a given force, let's say I used 10 newtons on several different springs. Some springs will stretch more for the same 10 newtons, and some springs will stretch less for that same 10 newtons. So therefore, each value of K will be different for each spring. When the value of K for a spring is a high value, that spring is called a tight spring. And when the value of K is small, that is a loose spring. Tight springs are difficult to stretch. Loose springs are easy to stretch. If we return to the simulation and pick up where we left off, you can see that I have applied a force of 100 newtons to the right, which is this orange vector. I've caused a stretch of 0.5 meters in a spring that has a K value of 200 newtons per meter. So if I do basic math, you can see that this 100 newtons is the applied force. And if I divide it by the 0.5 meters that it stretched, That gives me 200 newtons per meter K value. Sometimes you know the K value and you want to find the elongation or the force required to cause an elongation. Sometimes you know the force and the elongation and you simply want to determine the K value for the spring. It all depends on what you have and what you're looking to solve for. Let's do a brief discussion on the energy that's involved in elongating a spring. In order to determine the energy stored in a spring, we first have to realize the derivation of the equation is simply based on the comparison of the force to stretch ratio. If we place the applied force on the y-axis and the elongation on the x-axis, then we realize that the slope of this line is K, the pull to stretch ratio. What about the area under this line? Well, we know that the area of a triangle is 1/2 base times height. And the base is x for elongation, and the height is the spring force. So if we replace the base with x and the height with the spring force, we get 1/2 x times the spring force. And if the spring force is written out as kx, you can clearly see that it's 1/2 kx squared. So that area under the graph is in fact the work done in stretching the spring and also the energy that is stored in the spring. When a spring is elongated, the worker is pulling against the spring coil. The invested energy into the spring is stored as elastic potential energy. Releasing the spring, that energy is converted into kinetic energy. Just imagine a bow and arrow releasing the arrow, or a slingshot setting a pebble in motion. And then, of course, as we just explained, the area under the curve is the work done in stretching that spring. You can now clearly see that the only two equations on the reference table for springs are equations 15 and 16, the elastic spring force and the elastic spring energy. Both involve K and X, which is the elongation. Here we are back at the simulation. This time, we will set the spring constant to 100 newtons per meter, and we will begin to pull this spring to the right, and as we watch the spring elongate, we will also see the potential energy of the spring rise. When we get to the final extension, I'll do a simple calculation for you, and you can see that it all works out. Before we begin, let me show you around the screen of the simulation. Here we have, as before, the claw which grabs the end of the spring. The green dashed line is the equilibrium position. Now you'll see there is the force to displacement graph, and underneath it you're going to see the area filled in, which is the potential energy. Also over here on the side we have a bar graph. So this bar graph will rise and match the area filled in under the line, which is F equals kx. I'm setting the spring constant to 100 newtons per meter, and I intend to displace this spring a full 1 meter to the right. So I will clamp the spring and I will begin pulling it to the right. You can see that the applied force that I'm pulling with is increasing. An orange vector to the right, I'm around 65 newtons as it is, and I'm pulling to the right, and as I pull to the right, you can see the blue area under the graph increasing. You could see the bar graph also increasing. You could see the elongation is increasing. So when I extend this fully to 1 meter displacement, you can see that 1 meter is marked here on the x-axis for displacement. You can see that the applied force is 100 newtons, matching the scale here below, and also matching the applied force vector here. And then you can see that this blue area is matched by this blue bar graph at 50 joules. Let's do some quick calculations to show you that the math works. The first quick calculation we'll make is the spring constant K. Here I have it set to 100 newtons per meter. So let's verify. If K equals F divided by X, we have 100 newtons divided by a 1 meter extension, 100 newtons per 1 meter. And that is correct. The spring constant is 100 newtons per meter. Now, as a quick check, I could show you that if I backed the spring down to a displacement of 0.5 meters, it only required 50 newtons of force. and 50 divided by 0.5 is still 100 newtons per meter. So the proportionality remains the same throughout the entire extension of the spring. Now let's return to the full extension value of 1 meter being pulled by 100 newtons. Let's use 1/2 kx squared to prove that it is a 50 joule potential energy storage. So we know that it is 1/2 kx squared. K is a value of 100 newtons per meter. And of course, x is 1. So 1 squared times half of 100, which is 50 joules. I chose these numbers because they're very easy and you could see them without having to write them down. So in conclusion, you can see that these equations 15 and 16 are used to find the spring constant and the stored potential energy in an elongated spring. In the next video, we will discuss the conservation of energy in an elastic body, but for now we will conclude with Hooke's law and the concept of the spring constant as the pull-to-stretch ratio. I hope you enjoyed this video, and I thank you for watching. We'll see you in the next video.